Okay, let's look at problem which is about specific heat at high temperatures. Here's the problem we are tackling. Imagine a single particle that can exist in just two states. These states have energies of 0 and E respectively. The question asks at high temperatures, specifically where Kb times T is much greater than E, what will the specific heat of this system, which we call Cv, be approximately proportional to? We have four options: proportional to 1 over T, proportional to 1 over T squared, proportional to e to the power of e over kBt, or constant. Alright, let's dive into finding the solution. First, we need to remember the definition of specific heat at constant volume, or Cv. It's given by the derivative of the average energy of the system with respect to temperature keeping the volume constant. The formula looks like this. Cv equals the partial derivative of the average energy written as angled brackets around E with respect to T, all while keeping V constant. In our specific problem, we have a single particle that can occupy one of two energy states, one with energy E1 which is 0 and another with energy E2 which is E. To find the average energy, we first need the partition function. The partition function, usually denoted by Z, is a fundamental quantity in statistical mechanics. For a system like ours, it's defined as the sum over all possible states of e to the power of minus beta times the energy of that state. So for our two states, the partition function z is e to the power of minus beta times 0 plus e to the power of minus beta times e. Since e to the power of 0 is just 1, this simplifies nicely to z equals 1 plus e to the power of minus beta e. Remember, beta is a common substitution in statistical mechanics and it's equal to 1 over kb times t. Now that we have the partition function, we can calculate the average energy of the system. The average energy is given by this standard formula, using the negative derivative of the natural logarithm of the partition function with respect to beta. Substituting our specific expression for z, we set up the calculation. Performing the differentiation, which uses the chain rule, results in this intermediate expression. Notice the two minus signs cancel out, simplifying the result to this form. We can also rewrite this by dividing the numerator and denominator by e to the power of minus beta e, giving us this final alternative expression for the average energy. Our goal is to find Cv, which is the derivative of the average energy with respect to temperature. Since the average energy is given in terms of beta and beta is related to T, we can use the chain rule as shown here. Cv is the partial derivative of average energy with respect to beta multiplied by the partial derivative of beta with respect to T. Let's look at each of these terms. First, we need the partial derivative of the average energy with respect to beta. Recall the expression for the average energy shown on the slide. Using the quotient rule to differentiate this with respect to beta gives us the expression shown. We get minus e squared times e to the power of beta, e divided by the quantity e to the power of beta e plus 1 all squared. Next, we need the partial derivative of beta with respect to t. Beta is defined as 1 over kb times t. Differentiating this simple expression with respect to t gives us minus 1 over kb t squared. We now have the two components needed for the chain rule calculation of Cv. Combining these two derivatives using the chain rule gives us the expression for Cv. As you can see, the minus signs cancel, resulting in this first exact form for the specific heat. We can also rewrite the denominator term using algebraic manipulation. By factoring and recognizing the definition of the hyperbolic cosine function, we arrive at this alternative expression. Both forms shown on the slide are equivalent and correct. Alright, the problem asks for the specific heat at high temperatures. In this context, high temperature means kBT is much greater than E, which implies beta E is much less than 1. So we are evaluating the expression in the limit as beta E approaches 0. When a value x is very small, we can approximate the exponential function e to the power of x using its Taylor expansion, which starts with 1 plus x. We'll use this small argument approximation with x equal to beta E in the specific heat formula shown on the slide. Let's look at the numerator. As beta E approaches 0, e to the power of beta E approaches 1. So the numerator simplifies to e squared times 1, which is just e squared. Now consider the denominator. The term inside the parentheses is e to the power of beta E plus 1. As beta E approaches 0, e to the power of beta E approaches 1, so the parenthesis becomes 1 plus 1, which is 2. Squaring this gives 4. Therefore, in the high temperature limit, the denominator simplifies to kBT squared times 4. Putting the approximate numerator and denominator together at high temperatures, Cv is approximately E squared divided by 4 kBT squared. Since E squared and 4 kB are all constants for a given system, this expression shows that Cv is approximately proportional to 1 over T squared. So to summarize, at high temperatures where Kb times T is much greater than E, we found that the specific heat Cv is approximately proportional to 1 over T squared. This corresponds directly to option number 2 in the original problem statement. Therefore, the specific heat of the system Cv will be approximately proportional to 1 over T squared at high temperatures.